All right, so waiting.
Yeah,
So really nice to see you back again, Radovan. So that was, I think it was 1 year that we can go. Okay, go, we're live. So I think Radovan is a good colleague of mine, Redhead. He's a software engineer for OptaPlanner. I'm looking here on the slides for like what is the formal presentation here. Has more than 10 years on experience on IT industry with business automation portfolio optimization. So he's going to present us the optimization AI Java made easy with OptaPlanner. I had the pleasure to meet Radovan last, I think it was 2 years ago, right, Radovan?
yeah.
So we worked together in a project, and Radovan is a really experienced guy with OptaPlanner. So let's go deep dive in. So, Radovan, the stage is all yours with your presentation. We'll be back on Q&A at the end. If you have any problems or anything, just I will be I will be on chat on mute. All right. So, good luck and see you.
Thank you very much. Hello, everyone. Welcome to this session. My name is Radovan Synek. I work as a core OptaPlanner developer, and today I would like to talk about optimization AI in Java and how to make the job easier with the OptaPlanner. First of all, why we should care about optimization AI? The answer is quite simple. There is a whole lot of optimization problems around us. Take a look here. We have some shared equipment and we want schedule access to this shared equipment to maximize its utilization because the company put a lot of money into the equipment and it also has probably a limited lifetime. Or we might be interested in optimizing execution of jobs that depend on each other. And our goal is to minimize the make span of the entire project. Maybe we run a fleet of vehicles and we have some customers waiting for package delivery. We want to minimize the driving time and the fuel consumption. In the cloud computing, we have some hardware, and this hardware has some capacity of resources like CPU and memory, and we are supposed to schedule execution of processes to run on this hardware, which demand some of these resources, some CPU, some memory. And we want to operate the cloud as efficiently as possible. So we want to minimize fragmentation of the hardware resources. Imagine we run a hospital. We have nurses, we have doctors, a lot of different departments. And our goal is to schedule shift for the nurses and doctors. We want to take into account their specialization, their skills, but also their preferences. Somebody might be interested in having a night shift on Thursdays, for example, or one nurse demands a PTO entire week in the next month. Also, we want to maintain fairness to keep our employees happy. Optimization AI is one of the most profitable AI disciplines. For example, the vehicle routing can save even hundreds of millions of US dollars per year to some big companies. This is all nice, but how should we proceed if we want to optimize a new planning problem? We are in the middle of the summer and classrooms look like this. No teachers, no students. Soon this is going to change, and the first thing the school staff has to come up with is to create a new timetable for the next school year. What does this job involve? We have students organized into groups, like 9th grade. And these groups of students are supposed to take lessons of some subjects, and the lessons are taught by some teachers, like Mr. Turing here is teaching math. We also have some rooms where the lessons should take place, and some time slots. Now we need to take all the data into consideration and produce something like this. Here we can see, for example, that the lesson of math by Alan Turing is supposed to take place at 8:30 in the room A. Sure, this one was easy, because we have just 4 lessons, 2 rooms, 2 time slots, and 2 student groups. This is not really the case of real high schools. They deal with tens of lessons, tens of rooms, student groups, and teachers. Also, we usually have to use the entire work week. So to come up with a real high school's timetable can take easily even days. It would be nice if teachers didn't have to go over this exercise year after year. Sure, applications that are capable of generating a school timetable already exist. Today, we will see how to create such an application using the OptaPlanner. So this is what we are interested in. A web application where we just define the rooms, time slots, and lessons, and it will generate the timetable for us. Let's take a look at the architecture of the application. It's a web application, so there will be some web page to show the timetable. The web page communicates with a REST API. We also have some database to store the results to. And of course, there is the OptaPlanner. The entire application runs on top of Quarkus, which provides a quick redeploy, minimal memory footprint, and also the possibility to compile the application into a native image. But for this talk, I would like to focus just on this box over here, the OptaPlanner itself. OptaPlanner is written purely in Java. It's an open source project which has been around for over 10 years. If you open the documentation, the first thing you learn, and let me just read it aloud, it's a lightweight, embeddable constraint satisfaction engine which optimizes planning problems. That's quite long definition. First, let's take a look for what the planning problems are. What's typical for planning problems? Each planning problem has its specific goals. Let me show you on the example of vehicle routing. Here, our goal is to minimize the fuel consumption and also the ecological footprint. It's nice if we can save both the money and the environment. Usually there are some resources that participate in the planning problem. Here we have the vehicles. An important thing is these resources are always limited. We also have some constraints on the resulting solution of the planning problem, like here the vehicle capacity, which tells us that each vehicle has a maximum capacity of what it can carry at any moment. And the driving distance of vehicle, that's what we try to minimize, because this is This is directly connected with our goal to minimize the fuel consumption. Now, bad news about planning problem is that planning problems are difficult to solve. In terms, there is no guarantee of finding the optimal solution in reasonable time. The issue is that the planning problems don't scale well. So if we want to use brute force search algorithms for other than trivial problem sizes, it won't work because they may easily take thousands of years to finish. We don't want to wait for so long. Now, good news about planning problems is that using constraint solvers like OptaPlanner, we can find near optimal solution in a reasonable time. And once we have a solution, we can quickly verify if the solution is good enough because we know our goals, we know all the constraints. Before jumping to using OptaPlanner, let's first check if the school timetabling is a planning problem. All right, what are our goals? Maybe we want to make both students and teachers happy. Or let me reverse it. We don't want to make them suffer. Imagine you have a timetable full of gaps between lessons, so that you have to wait between the lessons before the next one. That's really not favorable. What are our limited resources? We have a fixed amount of rooms and we have a fixed amount of time slots. And can we figure out some constraints we might have on the solution? So for example, we want to schedule all the lessons that are supposed to be taught. And we have also some limitations of the physical world. Like at any moment, there can't be two lessons taught by the same teacher. And the same applies to the rooms, as there can't be two lessons taking place in the same room at the same time slot. Sorry. And also we want to, as I already said, minimize the gaps between lessons. All right, so we were able to identify some goals, some limited resources, and constraints. So this really looks like a valid planning problem. OptaPlanner should help us with solving it. Now, if we understand the planning problem, we also need to make OptaPlanner understand it, the nature of the problem itself, and our constraints. As we are talking about optimization AI in Java, we will define our planning problem as a set of Java classes. And when we are creating this problem domain, we have to ask ourselves questions. What is the entity that changes during solving, the planning entity? And in this planning entity, in this class, what references should OptaPlanner change for us there? These are the planning variables, because this is really what OptaPlanner does. It changes values of the planning variables. It puts their different instances to these references. And each time such a change creates a new working solution. And for the new working solution, we have to be able to tell how good the solution is, which leads us to the constraints. Constraints are capable of calculating score of any solution. To implement our constraints, we can use the Constraint Streams API. which is Java API inspired by both Java 8 streams and also by the SQL syntax. When we are designing our constraints, we also have to choose which are hard and which are soft. Hard constraints must never ever be broken. If we break hard constraints, our solution is not feasible. Hard constraints are usually used to modeling limitations of the physical world. Here, as I said, we cannot have a conflict on the rooms. So we cannot have two lessons taking place in a single room at any moment. So this is a typical example of a hard constraint. If such a situation occurs, our timetable simply isn't valid. On the other hand, our desire to minimize gaps between lessons is a soft constraint because it can be broken. We want to minimize occurrences of the gaps, but if they happen a couple of times, we can probably live with that. Soft constraints are usually used to model cost of the solution. Enough theory, let's get back to the design and implementation of the timetabling application. Here is the class diagram. So again, this is the first step we have to do to describe the planning problem, to create our problem domain. So we have three classes. The first one is the time slot. It's associated with a day of the week. It has some start time and end time. Next, we have the room. And the last one is the lesson. The lesson has some subject, a teacher, and a student group. It also has two references, one to the time slot and one to the room. Now, OptaPlanner's job is to assign instances of the time slot class and of the room class to these two references of the instances of the lesson class so that the resulting solution breaks as few constraints as possible. Our job as developers is to tell OptaPlanner that the lesson is our planning entity and the time slot and room are the planning variables. Let's have a closer look. First of all, let me run the application. We run on top of Quarkus, so if I run this command, maven clean compile Quarkus dev, it should start the application in a development mode, so I don't need to care about redeploys if I make any changes. And here we go. Here is the UI of the application. We have three rooms, A, B, and C. We also have a couple of time slots. Here below, we have all the lessons. At this moment, the lessons haven't been assigned yet. Here we have the score of our solution. The -40 init signalizes the solution hasn't been initialized yet. Where does this number actually comes from? If we take a look, we have 7, 14, 20 unassigned lessons. And remember, each lesson has two planning variables, the room and the time slot. So the minus 40 means we have exactly 40 uninitialized references to planning variables. Let's run the solving and see what happens. As you can see, the minus 40 in it disappeared, and we have just the hard and soft score, which describes our solution. So 0 hard means we have no hard constraints broken, and we have actually positive soft score. That's fine. The solution is initialized. There are no unassigned lessons left. Now, let's check the result. If we take a look, there is no conflict on the rooms. So each lesson is taking place in a different room at any moment. That's fine. For student groups, no problem again. Let's check the teachers. And this is clearly not good. This is a conflict. Here, Mr. Turing is giving lesson of math to both 9th grade and 10th grade student group at 8:30. There is no way Mr. Turing is capable of doing it, so this is definitely a problem we should solve. But our hard score is 0, it's not below 0, so we probably have some issue in our constraint implementation. Let's have a look. First, let me show you the domain of our timetabling application. So again, this is the lesson class. It's marked with the planning entity annotation. And here we have the references to planning variables, the time slot and room, and here are the annotations. The annotation has one parameter, which is a reference to value range provider. So this actually tells OptaPlanner where to take all the eligible values for this planning variable from. Now, what is the source of this reference? For that, I have to show you one class I haven't talked about yet, and that's the timetable, which is annotated with the planning solution annotation. The planning solution usually wraps all the information about our planning problem so that we have here, for example, list of all time slots. And it's annotated with value range provider. The ID is time slot range, which matches this parameter here. So this is our source of the possible values of time slots. Similarly, we have a list of all rooms, also annotated as value range provider. And we also have a list of all lessons. And it's our planning entity collection property. So this annotation tells OptaPlanner that this field contains all the instances of the planning entity. The solution also has a score associated with it, which describes how good the solution is. Now, what happens if we click on the solve button? So the web page sends a request to REST API, which is handled by this REST endpoint. And here, as we run on top of Quarkus, and we have the OptaPlanner Quarkus extension on the class path, the only thing we have to do is to inject the Solver Manager. Solver Manager is an API used for submitting problems for optimization. The API takes two type parameters. The first one is the timetable, or planning solution. The second one is long, and its problem ID. It's a number, or generally an identifier, which helps us identify the planning problem which is being solved. And this is the method which serves the solve button. Here we use the solver manager, and we call a method called solve and listen. Because the solving takes some time, it's a continuous process as the solution evolves. And this method takes three parameters. The first one is the planning problem ID, the identifier. The second one is a method reference. And it's about the input for OptaPlanner. Because before OptaPlanner starts solving anything, it needs to load the input planning problem. So it will call this method. And if we take a look, the find by ID actually queries all the time slots, rooms, and lessons from the database and creates a new instance of the timetable. As the first method reference deals with the input, the second one, the save method, deals with the output. Every time OptaPlanner creates a new best solution, which means it was capable of improving the solution further to attain a higher score, it has to do something with the new best solution. So it will call this method. And this method will just again save the new best solution into the database. But we have no issue with the domain, nor with the REST endpoint. We suspect our issues lie within the constraints. This class, timetable constraint provider, uses the constraint streams API. Here we define all the constraints. So this is the method we have to implement. The method takes a single parameter, constraint factory, and returns an array of constraints. It's recommended to define each constraint in a separate method just for better readability. So here, for example, we have the room conflict constraint. Again, this is about the fact that at any moment there can be up to a single lesson in any room. As I said, the constraint streams API was inspired by Java streams and also by SQL. So if we start with from, which reminds us of the SQL syntax, and we pass here a class, the lesson, because this constraint can be translated as we are looking for pairs of lessons that happen in the same time slot and take place in the same room. So what do? We want to have pairs of lessons. From gives us something called unique constraint stream of the lesson. Stream of lessons, basically. Now we join lesson again, which creates a by constraint stream of types lesson and lesson again. If we did just the from and join, the result would be complete Cartesian product. But we are not interested in Cartesian product. We want something a bit different. So we will use joiners. We will somehow limit the combinations. We can take the equal joiner and the equal joiner takes some function which adds the type in the stream, the lesson, to some property. So here we can use method reference and use the getter of the time slot. By this, we join just the lessons that happen in the same time slot. And similarly, we use the same kind of joiner to join lessons that take place in the same room. Also, we don't want to have pairs of the same lessons. We only want to have pairs of two different lessons in the stream. So we filter and we allow in the stream only lessons that are different. And every time we detect such a pair of two different lessons that happen in the same time slot and in the same room, we penalize the solution for the room conflict constraint and for 1 point of hard score, because this is our hard constraint. This should not be broken. If such a pair of lessons exist, our timetable is invalid. As you can see, the teacher conflict, which is exactly what we are facing here, hasn't been implemented yet. Let's give it a try. We will return something we create from the constraint factory. And here I could start with from and join again, but I will do something else. I will use from unique pair. Why? Because this is the same situation as with this constraint. Again, we need to detect pairs of different lessons that happen in the same time slot, but this time the lessons are taught by the same teacher. So what do I put here? Lesson class. Now I have a stream, by constraint stream, of pairs of different lessons. I will use the joiners to limit our stream. And how do I want to join the lessons into pairs? It's about something happening in the same time slot. So the lessons should be assigned to the same time slot. And also, we are dealing with the teacher conflict, which means all lessons have the same teacher. And I'm going to analyze every such a solution which contains such a pair of lessons. And this is the teacher conflict constraint. Hard soft score. This is another hard constraint because, as we saw, this is something which should not happen. We can't have the same teacher giving the same lessons at the same moment. So this is hard constraint. I will analyze the solution with 1 point of hard score for every such a pair of lessons, for every occurrence. Which means if this happened, this is 1 point hard, another, we have already 2, 3, 4, 5, 6, 7 hard, minus 7 hard, because we penalize. If we take a look at different constraints, we don't have to only penalize, we also may reward the solution. If we detect something which is favorable, like here, this constraint is about teacher time efficiency, about the fact that teachers would prefer to teach lessons sequentially. We want to avoid gaps. That's something we thought about when we were discussing goals of timetabling. We can actually define constraints in the positive manner so that we reward the solution. And as you can see, we can also mix the two approaches. So for some constraints, I penalize the solution. For others, I reward it. All right, so let's quickly recap our teacher conflict. We have a unique pair of lessons which take place at the same time slot and are taught by the same teacher, and we penalize it. That should be it. We uncommented the method. Let's give it a try. Let me just rerun the solving. So again, OptaPlanner has quickly initialized the solution. As we are looking at the summarization by rooms, so far so good, no conflicts. Student groups, still okay. And the teachers, much better, isn't it? It works. No teacher is supposed to give 2 or more lessons at the same time slot. All right. Is there anything else we can do about this timetable? Let's have a look. For example, here, Madame Curie is starting in the Monday morning with the lesson of chemistry in the room C. Then she has to move to the room B to give a lesson of physics. And right after that, she has to move back to the room C for the chemistry again. And also Mr. Turing has to change the room only once. And other teachers seem to move between rooms as well. Let's do something about that. Let's say we want to define a new constraint, which we call teacher room stability. What is this constraint about? Teachers would prefer to stay in a single room. We want to avoid them moving between different rooms. In other words, we want to penalize any pair of different lessons that are taught by the same teacher, but happen in a different room, right? So I return something from the constraint factory. I will again start from the unique pair of lesson and I will use some joiners. So I want to join the two lessons into a pair based on a teacher. This is what the lessons are supposed to have in common, right? So I will use this method reference, lesson with teacher. I have a pair of different lessons that are taught by the same teacher. I cannot join the lessons based on inequality of some of their properties. So instead, I will use filter. the filter, look, it takes a by predicate. So it's a method which takes two inputs. As we are dealing with by stream of lesson, the both inputs are the lessons, or pair of lessons, and it returns a boolean. So we will provide this lambda, lesson 1 and lesson 2. And we want lessons that take place in different rooms. So lesson 1, get room equals, it does not equal lesson 2. And the last step, I have to analyze the solution for teacher rooms. And this time, I will use the soft score because it's a kind of preference of the teacher. We can live with that. Let me quickly check it. We return a constraint which deals with a unique pair of lessons that have the same teacher and that take place in different rooms. All right. Again, let's give it a try. Let me once again rerun the solution. Two lessons being already assigned, and as you can see, OptaPlanner is still doing some changes to improve the solution further. So no conflicts for the rooms, still okay. No conflicts for the teachers, still okay. No conflicts for the student groups, that's fine. And let's take a look. So now, Madame Curie is giving lessons on the room A. See? And similarly, Mr. Turing is giving lessons of math only in the room B. And other teachers also stay in the same room. All right, this looks like we have our perfect timetable. Hopefully everybody will be happy with that. Let me shortly recap of what we did. What are the typical steps if you want to optimize any problem with OptaPlanner? So first of all, after you identify your planning problem, you have to define the problem domain. You have to implement a couple of Java classes and decide what is the planning entity or planning entities. And there, what are the planning variables? Usually you wrap all the information about the planning problem into a planning solution. The next step is to implement the constraints. Remember, there are usually hard and soft constraints, and if you like Java, you can use the constraint streams API, like we did. The last step is just to submit your problem for solving. For that, we can use the Solver Manager API and the solve and listen method. All right, if you are interested in the OptaPlanner, please check its homepage. And if you want to play directly with OptaPlanner, feel free to clone it from GitHub. Thank you very much for your attention. I'm sorry, Guillermo, I cannot hear you.
Oh, my apologies. Probably you can now hear me, right?
Yeah, it's much better. Thank you.
Thank you, Radovan. It was a really, really nice presentation around OptaPlanner. It was a really deep dive into OptaPlanner. We can switch to Q&A. Kaina asked me on the chat if you wanted to show the repo from OptaPlanner.
Show the repo of OptaPlanner.
Right, that's something that she mentioned, to show the repo at the end. That is something
Sure.
that might be interesting for everyone.
Sure thing. I hope you can see it. Yes, so this is the OptaPlanner repository. A lot of modules. The most of the functionality I showed is covered by the OptaPlanner core. If you are interested specifically about this example, which I showed you, have a look at OptaPlanner Quick Starts. You will find the timetabling applications there running on top of Quarkus. You can play with that yourself directly.
Okay, that's nice. So we can switch over to the Q&A. Let's see, one of the questions is, does the AI Java have any advantage over using AI on the other programming languages like Python? That's one of the questions.
Yeah, like advantage. I'm not so familiar with the options on the Python environment or ecosystem. OptaPlanner, what are the strong pages of OptaPlanner? It's the advanced meta heuristics, local search algorithms, which are capable of providing the near optimal solution. OptaPlanner usually utilizes some basic algorithms in the first phase called construction heuristic to initialize the solution, to bring the solution from the minus something in it to fully initialized solution with a lot of constraints broken. From this moment, the local search algorithms start to improve the solution further and further with every step. Another strong page of OptaPlanner is real-time planning. It hasn't been shown in this example, but if you already have a complex solution and you are still improving it, and you may have incoming changes, small incremental changes to the solution, something like with the vehicle routing. For example, you add a new customer when the drivers are already on the road. Surely you don't want to rerun the entire solving from scratch. So OptaPlanner can process problem fact changes, these incremental changes, adjust the solution with the changes real time, and again, from that step to continue improving the solution further. Guillermo, I'm sorry, I cannot hear you again.
Oh, that time
Okay.
was on mute on the button, not on the microphone. My apologies again.
Okay.
So which library, one question is, which library was used for the timetable user interface, the UI part? That is one of the questions as well.
I think the combination of a couple of JavaScript libraries, including the famous jQuery.
Let me see what else here. One question, more general question here is, the client side, we haven't seen on this example, actually one before, can quantum computing be soon used for optimization problems? That is the more general question.
Sorry, I think I got a bit lost in the question. Could you please repeat it?
Can quantum computing be soon used for optimization problems? I think so, right? I mean,
quantum computing. Yeah, I get it. Possibly, yes. Like the optimization is, or let me fix the answer. Certainly, yes. Theoretically, and please take it with the salt of grain, because I'm definitely not someone who should talk on a conference about quantum computing. But optimization is about searching a huge space of all the possible states, of all the possible solutions. It's about huge space of possible combinations. So yes, theoretically, this is what quantum computing could be used for.
Right, and two questions, I'm going to group them together. It's more about OptaPlanner. One is if it's currently being used at scale, like the person here suggests that an example that I can think is the music festivals during different performances and stages. It can be also a sample that can be used for the next conference here, for example, like music stages. And there is another one that if the OptaPlanner can be used on Android.
Yeah, so for the Android, I think there was some extension in the past. I'm not familiar with the current state of the extension. Generally, OptaPlanner does a lot of heavy lifting. If you run it, it can take at least a single CPU core. So I would rather recommend running it as some server-side application and to integrate it with the client. To answer the previous question regarding the other use cases, the simple answer is yes. And as I showed a couple of modules in the OptaPlanner repository, I will point you to another one, which is OptaPlanner examples. This shows all the examples which have been solved by OptaPlanner so far and incorporated in this repository. Don't get scared of it because it has old Swing UI, but usually if you have some planning problems and you don't know how to start, let's have a peek here. Maybe you will get some inspiration.
Right. Also, there is a mention here on the last question for the how efficient is OptaPlanner. There was a mention to the vehicle routing problem, and the question was how efficient is the OptaPlanner? There's a way to feed it with more data. So
yeah, how efficient OptaPlanner is, well, or rather, how does it scale, right? There are certainly some limitations regarding what time would you like to invest into solving and how good solution you expect, because for certain size of the problem and some expected outcome, you need to invest some time. You need to give some time to OptaPlanner to figure out a schedule. And if the problem is really large, there is a couple of ways how to deal with that. First of all, I would recommend another module of OptaPlanner, which is OptaPlanner Benchmark. It can help you to compare different configurations of OptaPlanner. This is about power tweaking. If you want to pick different algorithms, if you want to do some interesting optimizations of how OptaPlanner should proceed, the OptaPlanner benchmark will help you measure how good each approach is compared to each other. Also, there are techniques for really big data sets, like you can let OptaPlanner solve the big data set during the night, because, for example, with the vehicle routing, you have some orders to proceed, and the next morning the drivers should jump into the vehicles and start delivering packages. So you have entire night for solving. So let's get use of it. And this is where the real-time solving helps, because if during the day some changes arrive, you can again just react to these changes and you don't have to restart the entire solving.
Nice. So one question that I missed was if there is some sort of OptaPlanner API, like if the client side, we haven't seen the example, is coded in this project or is offered, I mean, if there is some way that we can use OptaPlanner as API, and if it's coded, which language that OptaPlanner does support?
Well, OptaPlanner is written purely in Java. So basically any language that is compatible with the JVM. So think, I don't know, Kotlin, Scala, Groovy, and of course Java itself. And the API to use, I have shown the Solver Manager API, which is a bit higher level, but there is also Solver API. It doesn't take these lambdas or method references to deal with the input and output. It's something you have to deal with yourself. It also doesn't process multiple data sets in different threads as the Solver Manager. So it just takes a single thread. Yeah, these are basically the two APIs for submitting the solving input.
Nice. Was really great to hear. I hope we covered all the Q&A. Radovan, we can share your contacts for everybody to reach out after that if there is any other further questions, and then we can move forward. Thank you for your presentation, Radovan. It was really nice to see you. And let's switch gears. Thank you.
Thank you, everyone. Goodbye.
Bye.